Ladies and gentlemen, in this tutorial video we're going to cover entropy, what it is, as well as how to do some sample calculations for delta S, the change in standard enthalpy. As it says here on the slide, entropy is defined as a measure of the disorder in a system. Some folks would like to call disorder chaos. I've heard other professors and teachers say that chaos is not the right word. But the idea is that we want to look at it in terms of disorder. Are things randomly arranged, or are they very organized? So we would say entropy, if something is high in entropy, it has a lot of disorder. If it's low in entropy, then it's quite organized. In fact, the natural state of the universe is such that there is a high entropy. So we would expect for a large amount of disorder in terms of particles. Entropy uses delta S to represent the change in entropy. And if we're talking about entropy being about the amount of disorder in a system, there are three factors that would increase entropy. They would increase the disorder. Change in physical state, going from solid to liquid or liquid to gas. And the reason is that solids in their physical state are much more compact and closely arranged, whereas in the gaseous form, they are more spread apart and freely moving. So if we can spread out the particles into a more random movement, then we are increasing entropy. The second one here, I'm going to switch to a pen. So that was the first one. The second one is, can we increase the motion of the particles? So can we get them to move faster, perhaps? So what's one way that we can increase the motion of particles? How can we make them move more or faster? Heat. So if we increase the temperature, theoretically, we could increase the motion of the particles. And then the third one here is increasing the number of particles involved. If you have more particles, there's going to be a greater amount of disorder. So if we go and do a chemical reaction and we have 2 of A, and it does a reaction, and we make 4 of B, well then entropy, delta S, trying to do this with a mouse, delta S is going to increase because we're going from 2 particles of A to 4 particles of B. We're increasing the number of particles in the system. Okay. So does this make sense? Right, we want to increase the disorder, the amount of randomness of the particles. The entropy that I gave you guys the other day is your room at home. Okay, is your bedroom at home clean and things put away? Or is it a mess like most teenagers' rooms? Okay, a big mess. So, we could argue that that is the natural state of the universe, a high amount of disorder or chaos, high entropy. In the universe, in terms of chemistry and physics, that's a good thing. At home under your parents' roof, that's a bad thing. Okay. The third bullet point, or fourth bullet point, we say that a positive delta S, so plus delta S, is more likely to occur because we want more entropy, we want more disorder, so that's going to be more likely to occur. And then a negative delta S, less likely to occur because we are decreasing disorder, or maybe we say we're increasing the order, how organized it is, which isn't always a good thing. Notice that the likely to occur part is opposite for delta H. Delta H for enthalpy, we said a negative exothermic is likely to occur, and here the likely to occur is a positive delta S, meaning we're increasing the disorder of the system. Yeah?
So when it says more likely to occur, that means the order is more likely?
The reaction.
The reaction is more likely than the order?
It's more likely to occur. It's more likely to happen, period. A chemical reaction. So any chemical reaction, if we can determine the entropy for it and say, oh, the entropy is negative, well, this reaction isn't very likely to take place. Okay, the likelihood, the probability is low. If entropy is positive, that means that we're increasing entropy, that we are increasing the disorder of the system when it reacts. That's a good thing. And so that would be likely to take place.
Increasing disorder could mean more stability?
Sure.
Is this for all reactions?
Now, there will be a caveat, and we'll look at this probably on Monday or Tuesday, is the idea of spontaneity. And so we actually have to consider enthalpy and entropy. And we'll see that if enthalpy and entropy are both likely to occur, then the reaction is likely to occur. If they're both not likely, then the reaction is not likely. But if they're opposite, so enthalpy is likely and entropy is not likely, then we're going to have to do some math to figure out which it is. Okay? So if they both match, then that tells you one way or the other. But if they're opposite, then we have to do some figuring out. We'll do that later. For now, let's look at how to calculate delta S. You're going to use your table of values, okay, your appendix 3 that I gave you, as well as a balanced chemical equation. And we have delta S naught, the standard enthalpy change or entropy change, is equal to the sum of the entropies for the products minus the sum of the entropies for the reactants. Looks familiar, right? Okay, so what we did for enthalpy and what you did on the quiz today, identical, except we're going to use different values. Okay?
Not the second column.
It is the second column. So I'll give you a second to jot that down, yeah.
So basically it's like the same thing with like different values in the end, the meaning.
Yeah, the meaning is negative and positive is flipped. The units will be different, and the numbers will be different, but how we calculate it's the same. Process is the same, yep. Greek letter sigma in sum. S U N. Okay? You guys got it down? Almost. All right, so I'm going to move on here. And I'm going to switch to this here. So what I did is I actually have, we'll look at number 3 here. This should look familiar. This was your standard enthalpy practice the other day, earlier this week. And so we're going to look at number 3 here. Remembering what we just said, delta S is equal to the sum of the products, S, minus the sum of the reactants. And we're using our appendix 3, right? So should look like this, right? We are using the second column for each of these, where delta S naught equals joule per mole Kelvin. So that's the unit over here. Which means that when we multiply it by our coefficient, which is a number of moles, the moles will cancel, and we are left with joules per Kelvin for the unit. Okay, and that's important. We'll see where the Kelvin comes in next week. Kelvin is temperature. So as I showed you before, let's look at each value from our appendix 3 and figure out what the value is. So I'll do the first one. methanol liquid, C3 or CH3OH liquid. Here we go. Delta S second column, negative 166.23. Okay, elements are not zero, only with enthalpy. So there should be a value here for entropy with elements. Yeah, we will have to. I'll come back to that real quick in a moment. So O2, oxygen. Where'd we go? Sorry about that. So O2 is 205. While we're on that side, water liquid is 69.91. And CO2 gas, 213.6. Okay, if we balance the equation, you have one carbon here, one right here. 4 hydrogens on the left, which means we need 2 waters on the right. And then we have 4 oxygens on the right. Shoot, we have an odd number over here. So this should actually be doubled. That's doubled. That's doubled. And now we have 8 O's. So we need 3 right here because we have 2 on the left plus 6 is 8. So 2, 3, 2, 4 for our coefficients. So then for delta S, we have our products. We have 2 times 213.6 plus 4 waters at 69.91 each minus our reactants, 2 times negative 166.23 plus 3 oxygens at 205 each. Right? We can put in our calculator. So here I'm going to do the left side first, the product side, which is that times. So 706.84 for the products minus you got 282.54. When we do that subtraction, we get 424.3, and our unit is joules per Kelvin. So this is a positive value. So is this reaction likely or unlikely to occur based on the entropy? More likely. Yep. Okay, make sense?
Yeah.
Okay, so we're going to give this a shot later. And that's it for today.